Last topic for chapter 13, and this is discussing Le Chatelier's principle. Le Chatelier's principle tells us that when a system is at equilibrium and you apply a stress, the equation will shift to regain that equilibrium, and it will shift in the direction that tends to reduce the change. There are three types of stressors of equilibrium, and they are temperature, concentration, and pressure. And we're going to take a look at how each of these will affect a reaction that is at equilibrium and talk about which way it would want to shift to minimize that stress that was applied. There are two videos that go over demonstrations with these principles on the Google site under chapter 13. There are two YouTube videos, and I will also do a demo in class to show the shifting. So let's talk about the first one, temperature. I guess before we talk about temperature, we're going to talk about two stressors that don't affect it. So if you apply a catalyst to the reaction or an inert gas like a noble gas, these will not affect reactions at equilibrium. Catalysts will simply make the reaction go faster, as we know from the prior chapter, but it will not have an effect on causing it to shift more one way or the other. Also, just keep in mind the only way to change the value of the equilibrium constant, so K, is to change the temperature. So now we can talk about effects of concentration changes on the system. So adding chemicals in a reaction. So if you want to add more of one reactant or product in the reaction, this will cause the reaction to shift away from the added component, because it will cause more reactions to happen on the side that you added it to, and so therefore those will react and make more of whatever is on the opposite side, and so it will shift it away from it. And then the opposite, if you were to remove a component in a reaction, the opposite effect will occur, and it will shift toward the side where it was removed from to make up for that loss. Usually if you add chemicals that aren't even in the reaction, you're not going to have an effect on equilibrium. However, sometimes if you add a chemical that will form like a precipitant, then this will actually take away that chemical, and you will have it shift in the direction that the reactant or product, whatever started to form a precipitant, the reaction will shift toward that to make up for the loss. So it's kind of like you're eating up or losing that particular compound. So if you add some other chemical that's not even in the reaction, and it will form a precipitant, so you have to go back and think about those darn solubility rules. But if it starts to eat up that reactant or product and form a precipitant with it, then the reaction will shift toward that in order to make up for the loss. Temperature. K will change depending on temperature. We've said that a lot this chapter. And you have to actually know what side temperature is on the reaction. So you'd have to be told. You'd have to say if it's endothermic or exothermic. And remember, endothermic, the energy is on the reactant side, and exothermic, the energies would be on the product side. Or maybe simply in the reaction, they'd give you a positive delta H or a negative delta H, just a number by the reaction, and a positive, remember, is endothermic, and a negative is exothermic. And so you can kind of imagine that positive energy goes on the reactant side and the negative energy would go on the product side. So here's an example of an exothermic reaction. You can see the heat is put on the product side. So we know that it is an exothermic reaction. If you were to add more heat, when heat is more added, so if you add more, it will cause this side of the reaction to increase in how its collisions are working, and as a result it will shift to the left, because anytime these react more, it'll produce whatever's on the opposite side. If you took away this heat, the opposite side will continue to have its collisions undisturbed and will keep making more of the opposite side, and this side would have slowed down because you had taken it away. So we would say that's a shift to the right to make up for or to compensate for what you just lost or slowed down. So again, if you have an exothermic system and you decide to add more, it will cause more collisions on that side and make more of the opposite side. We call that a shift left. If it was an endothermic reaction, you would have seen the heat over here, and endothermic, adding more of the temperature would cause it to shift to the right. It would cause more collisions over here. As a result, more product would be made. Pressure. Let's talk about what pressure will do. This is kind of a tricky one because you have to actually look at how many molecules are in the equation and decide which side has more molecules, and that side is going to be more affected. So if you increase the pressure, you're causing the molecules to have more collisions. The side that has the most molecules will actually start to collide more often because you're in a smaller space, so they'll see each other more often, and as a result, those collisions will produce more of whatever is on the opposite side. And then if you decrease the pressure, then the molecule, it will have the opposite effect. Usually if you add a noble gas or an inert gas, there's no effect on the equilibrium pressure. So you'll sometimes be asked, hey, what happens if I add helium to this reaction? Nothing. So decreasing the volume then, or decreasing that pressure, will cause the reaction to shift toward the side with fewer molecules. I'm just looking because it looks like I wrote something down wrong, but I'm just double checking. Oh, the other one was just talking about decreasing the volume, which is like increasing the pressure, so it would have the same effect. And then when pressure is decreased, the reaction will shift toward the side of the reaction with the greatest number of moles of gas. Here is an example. You have your PCl5 is in equilibrium with PCl3 and chlorine. This side of the reaction has 1 plus 1. You have 2 moles total on this side and 1 mole on this side. So if you were to increase the pressure, this side would start colliding more often, and as a result create more of this side. If you were to decrease the pressure, you can kind of think of it as, well, this side does not need to collide with anything, so decreasing the pressure is really not going to have an effect on this. So it'll continue to do its thing and produce this other side. But these two, decreasing the pressure, they're not going to see each other as often, and so their reaction rate is going to slow down. They're not going to collide as frequently, but this one will continue. So that's why we say it will shift toward the side with the greatest number of moles if you were to decrease the pressure. And another reminder, stressors don't include adding an inert gas or a catalyst. So a catalyst is only going to speed up the reaction. The only way to change that value of K, the equilibrium constant, would be to change the temperature. You know what, I'm going to go back. I think it was labeled wrong, the concentration one. Maybe not. It's probably okay. So we talked about concentration, we talked about temperature, and we talked about pressure. Let's just try a real example, and then I'll feel like we hit all the pieces of it. And this is a really good example in that it gives you the reaction, an equation, a balanced equation. Yep, is it balanced? Yes, and it gives you the energy there, so it's exothermic, it's on the product side. And then it's going to give you a series of questions. So what if you removed water? So if you took water away, I think I'll pause for a minute and you guys want to kind of give your best guess, and it should be on your notes, and then we'll talk about why. So what will happen if you remove the water? Which way will it shift? And hopefully your answer is shift left, because if you remove this, that will slow down this side. This side will continue to collide, these two molecules will, and make more of this side that was removed. Let's talk about increase in temperature. So you have an exothermic reaction. If you add more temperature, or more heat I should say, then this side causes more collisions to occur, and you'll have a shift to the left. How about helium? Adding helium, what do you think will happen? Hopefully you said nothing because, hopefully you said nothing will happen to the reaction because helium is an inert or noble gas, and those will have no effect on the reaction. Let's remove carbon monoxide. What way will that shift? We would say shift right. Hopefully you said that because these two would continue to react. This side would slow down. So this side will compensate for that loss and shift right to make more of it. How about if we tripled the volume of the container? So tripling the volume of the container would be very similar to reducing or decreasing the pressure of the reaction. So you've got 2 molecules here that collide, and you have 4 molecules here that collide. If you decrease the volume, or tripled the size of the container, if you increase the volume, you would force these molecules to have a harder time to collide because the container is now very big and you'd need all of them to find each other, where you just have 2 on this side and the odds of those colliding would be greater. So these 2 will continue to collide and make more of the other side. So that would be a shift right. And I thought there was one more, but there's not. Just kind of on a final note, if you had both sides of the reaction had equal number of molecules, so say 2 on the left and 2 on the right, and they said, hey, what would happen if you increase the pressure or decrease the pressure? And in that situation, nothing would happen since they're on they have the equal number of molecules on each side. So we'll do a demo in class, and then I have linked 2 YouTube videos for you to watch as well. And then the book does a nice job explaining it too. So that is the last concept for chapter 13.